Ambient temperature plays a critical role in determining the ampacity of electrical conductors. When performing ampacity calculations, it's essential to understand whether to use the average or maximum ambient temperature, how inspectors evaluate temperature, and the difference between ambient and surrounding temperatures. The ambient temperature used in ampacity calculations should typically be the maximum expected ambient temperature for the location where the conductors are installed. This is because a conductor's ampacity, which is its current carrying capacity, decreases as the ambient temperature increases. By using the maximum ambient temperature, engineers and electricians ensure that the conductors are adequately sized to handle the worst-case scenario, preventing overheating and potential hazards. Now, regarding guidelines for inspectors, there are no specific, universally mandated guidelines that dictate exactly how inspectors must evaluate ambient temperature. However, inspectors generally use their professional judgment to determine the maximum ambient temperature for a given location. This judgment is often informed by several factors, including historical weather data for the area, the prevailing climate type, and the specific location of the electrical installation within the building or structure. For example, an inspector might consider whether the conductors are located in a hot attic, a sunny outdoor location, or a cooler, shaded area. The terms ambient temperature and surrounding temperature are frequently used interchangeably in the field, but there's a subtle distinction. Ambient temperature refers specifically to the temperature of the air immediately surrounding the conductors. Surrounding temperature, on the other hand, encompasses the temperature of all objects in the vicinity of the conductors, including walls, ceilings, equipment, and other nearby surfaces. For ampacity calculations, the ambient temperature is the more relevant factor. This is because the air temperature directly influences the heat dissipation from the conductors and is therefore more representative of the thermal conditions the conductors will experience. Now let's consider the factors affecting conductor ampacity. Firstly, conductor size is a key determinant of ampacity. Larger conductors have a greater cross-sectional area, allowing them to carry more current without overheating. Secondly, the conductor material plays a role. Copper and aluminum are the most common conductor materials, with copper generally having a higher ampacity for a given size due to its lower resistance. Thirdly, the number of conductors in a raceway or cable affects ampacity. When multiple current-carrying conductors are bundled together, they generate more heat, reducing the ampacity of each individual conductor. Adjustment factors specified in the National Electrical Code, or NEC, account for this effect. Fourthly, the type of raceway or cable installation influences ampacity. Conductors installed in enclosed raceways, such as conduits, may have lower ampacities compared to those installed in open air, as the raceway can impede heat dissipation. And finally, the presence of insulation around the conductors affects ampacity. Different types of insulation have different temperature ratings, which limit the maximum operating temperature of the conductor. It is crucial to select conductors with insulation suitable for the expected operating temperature and ambient temperature conditions. When calculating ampacity, several sections of the NEC are particularly relevant. NEC Table 310.15b16 provides the allowable ampacities of insulated conductors rated up to 2000 volts, based on conductor size, insulation type, and temperature rating for not more than 3 current-carrying conductors in a raceway or cable or earth. Adjustment factors for ambient temperature are found in NEC Table 310.15b. These factors are used to reduce the allowable ampacity of conductors when the ambient temperature exceeds the temperature rating of the conductor's insulation. Correction factors for the number of current-carrying conductors in a raceway or cable are found in NEC Table 310.15b3. These factors reduce the allowable ampacity of conductors when more than 3 current-carrying conductors are bundled together. NEC Section 310.15 provides general requirements for ampacity calculations, including directing factors for various installation conditions. For example, if the ambient temperature is higher than 30 degrees Celsius or 86 degrees Fahrenheit, a correction factor must be applied to reduce the conductor's ampacity. Similarly, if more than 3 current-carrying conductors are bundled together in a raceway, an adjustment factor must be applied. Now let's work through an example to illustrate how to apply these concepts. Suppose you need to determine the ampacity of a number 12 American wire gauge or THHN copper conductor installed in a raceway in an area with a maximum ambient temperature of 40 degrees Celsius or 104 degrees Fahrenheit with 6 current carrying conductors in the same raceway. Step 1. Determine the base ampacity of the number 12 AWG THHN conductor from NEC table 310.15b16. For a 75 degrees Celsius rated conductor, the base ampacity is 30 amps. Step 2. Determine the temperature correction factor from NEC table 310.15 bone. For a THHN conductor with a 75 degrees Celsius rating and an ambient temperature of 40 degrees Celsius, the correction factor is 0.87. Step 3. Determine the adjustment factor for the number of current carrying conductors from NEC table 310.15b3. For 6 current carrying conductors, the adjustment factor is 0.80. Step 4. Calculate the adjusted ampacity by multiplying the base ampacity by the temperature correction factor and the adjustment factor for the number of conductors. Adjusted ampacity equals 30 amps times 0.87 times 0.80, which equals 20.88 amps. Therefore, the adjusted ampacity of the number 12 AWG THHN conductor in this scenario is approximately 20.88 amp. Now let's explore some common mistakes to avoid when calculating ampacity. One common mistake is failing to account for ambient temperature correction. Ignoring the ambient temperature and its impact on ampacity can lead to undersized conductors and potential overheating. Another mistake is neglecting conductor bundling dirting. Failing to apply the appropriate adjustment factors for the number of current carrying conductors in a raceway can result in conductors operating above their rated ampacity. Another mistake is using the wrong temperature rating for the conductor insulation. Using the wrong temperature rating or not knowing it will result in conductors not being properly sized for the load that it will handle. A final mistake is neglecting voltage drop calculations. While not directly related to ampacity, voltage drop can affect the performance of electrical equipment. Conductors should be sized to minimize voltage drop and ensure proper equipment operation. In conclusion, accurately calculating ampacity is crucial for ensuring the safety and reliability of electrical systems. By understanding the impact of ambient temperature, conductor size, conductor material, conductor bundling, raceway type, and insulation type, and by carefully applying the relevant sections of the NEC, engineers and electricians can properly size conductors and prevent potential hazards. Always consult the latest edition of the NEC and seek guidance from qualified professionals when performing ampacity calculations.